1 minute ago, astronomers captured new images of 3I Atlas, an interstellar visitor speeding through our solar system. The shock is that it is showing non-gravitational acceleration, but not the massive coma or dusty tail science demands. This directly confirms the headline, "Something is happening right now that contradicts physics you learned in school." What could move a 6-kilometer object tens of thousands of kilometers off course without leaving any visible trace? The stakes are huge, and the next chapter begins with numbers no one expected. In 2025, the Hubble Space Telescope captured a series of high-resolution images of 3I Atlas as it entered the inner solar system. The object's appearance was striking for its simplicity, a compact, star-like point with no sign of a halo or trailing dust. Even as it approached the Sun, the surface remained smooth and featureless in the data. No diffuse glow, no faint arc, no evidence of the classic cometary coma that signals outgassing. Hubble's sensitive optics, capable of detecting the faintest wisps of gas or dust, found none. Every measurement pointed to the same conclusion. Atlas was visually unchanged, presenting a clean, sharply defined profile against the background stars. This baseline, established months before perihelion, set a clear expectation. In the world of comet science, a body of this size and trajectory, moving closer to the Sun, should have begun to shed material. The heat typically triggers jets of vapor and dust, building a bright, expanding envelope visible across the electromagnetic spectrum. Yet, image after image, the object defied these norms. The July data became a quiet reference point, a record of what Atlas looked like before any dramatic transformation. Scientists tracked its every move, waiting for the first hint of activity, but the object remained stubbornly unchanged. This visual certainty, captured in the heart of summer, would soon become the yardstick for everything that followed as the numbers and anomalies began to accumulate. The numbers behind 3I Atlas's motion tell a story that images alone cannot reveal. Modern observatories track its position with such precision that even the smallest deviations stand out. In early November, astrometric measurements showed Atlas was drifting off its predicted path by about 4 arcseconds, an offset that, at a distance of 203 million kilometers, translates to a physical displacement of nearly 80,000 kilometers in just 1 month. This is not a subtle effect. It is a measurable, persistent push acting on a 6-kilometer wide body sailing through the solar system. The cause is not gravity. Calculations show a net acceleration of roughly 0.02 millimeters per second squared, enough to nudge the object's trajectory by twice the distance from Earth to the Moon over 30 days. Breaking it down further, the force splits into 2 main components. About 135 kilometers per day squared directed radially, and another 60 kilometers per day squared acting laterally. These are not random jitters, but steady, directional changes that match what you would expect if something were providing a continuous, gentle thrust. Picture a ball rolling across a table. Gravity and momentum alone would carry it in a straight line. But if tiny, invisible thrusters fired along its surface, the ball would veer off course, and the path would no longer match the predictions of gravity alone. For Atlas, the deviation is not theoretical. It is written into the sky, tracked night after night by telescopes around the world. The challenge now is to explain what is doing the pushing and why the effect is so large without leaving a visible trace. On October 30th, 2025, 3I Atlas reached its closest point to the Sun, a moment known as perihelion. The timing should have triggered activity, but Atlas remained compact and unchanging, just as it had months earlier. The object continued on its outbound arc, setting up a series of key milestones for the months ahead. On December 19th, 2025, Atlas will make its closest approach to Earth, passing at a distance of about 167 million miles, roughly the same as the average gap between Earth and the Sun. This distance is still far beyond any threat, but it is close enough for telescopes around the world and in space to capture the most detailed data possible. Observatories have already scheduled observation slots, aiming to catch any sign of change in the object's behavior or appearance. This window offers the best hope for detecting the outgassing or dust release that would confirm a natural explanation for Atlas's odd trajectory. After this brief encounter with Earth's neighborhood, the object will continue its journey toward Jupiter. Around March 2026, Atlas will pass within range of the giant planet's gravitational influence. Astronomers predict this will be the last significant perturbation to its path before it exits the solar system for good. Despite its dramatic deviation from predicted orbits, calculations confirm there is no risk of impact with either Earth or Jupiter. The object's course is being monitored with extreme precision. The only thing at stake is our understanding, not our safety. These dates, perihelion at the end of October, closest Earth approach in December, and Jupiter in March, form the backbone of the observation campaign. Each milestone is a checkpoint, a chance to test competing theories about what is driving Atlas. With the clock ticking, the coming months will determine whether nature or something more unusual is at work. The numbers behind the Atlas mystery start with a simple equation. To push a 6-kilometer wide object off course by tens of thousands of kilometers in a month, something must deliver a tremendous amount of momentum. The measured non-gravitational acceleration, about 0.02 millimeters per second squared, cannot be brushed aside as a rounding error. For an object with a mass of at least 33 billion tons, that acceleration translates into a required force that, in cometary terms, only comes from outgassing, jets of vapor and dust erupting from the surface, acting like natural thrusters. But the math is unforgiving. To generate a push of this magnitude, Atlas would need to lose at least 1/6 of its total mass, over 5.5 billion tons, in a matter of weeks. That is more mass than many comets lose in their entire lifetimes, and it is not a subtle process. When a comet sheds material at this rate, the result is a vast, bright coma and a dust tail stretching for millions of kilometers. Even modest telescopes should spot such a spectacle with ease. Observatories are tuned to detect the faintest traces of gas and dust in the solar system. If Atlas is venting billions of tons, the evidence should be overwhelming. An unmistakable halo, a surge in brightness, a flood of spectral lines from molecules torn free by sunlight. Yet so far, every image and spectrum has come up empty. The numbers demand a show of force, but the sky remains silent. This is not just a technicality, it is a direct, testable prediction. If the natural outgassing model holds, the next round of observations must reveal a dramatic transformation. If not, the case for conventional comet physics will be on the line. Across observatories and continents, the response to 3I Atlas has become a coordinated campaign. From late November 2025 through January 2026, an international network of telescopes will keep the object under near-constant scrutiny. The James Webb Space Telescope has allocated precious infrared time, aiming to pierce the faintest traces of gas or dust that might betray a hidden outburst. Hubble will continue its high-resolution imaging, searching for any change from the compact, coma-free appearance that has so far defined Atlas. On the ground, major observatories, Keck, VLT, Subaru, Gemini, and dozens of smaller scopes will rotate through photometry, spectroscopy, and polarimetry, each method tuned to catch a different signature of activity or composition. Spectroscopic teams are preparing to scan for the telltale fingerprints of water, carbon monoxide, and more exotic volatiles. If any gas is escaping, even at a fraction of the required rate, it should light up the detectors with distinct emission lines. Polarimetry experts will measure how sunlight scatters off any dust grains, hoping to spot the unique polarization signature already hinted at in early reports. Every facility is working from a common checklist: detect a coma, measure its brightness, resolve the chemical makeup, and track any evolution in real time. The observing window is narrow. Atlas will be closest to Earth on December 19, 2025, and every hour of clear weather or open schedule counts. Behind the scenes, data pipelines are being calibrated for maximum sensitivity. Observers are running simulations to set detection thresholds, ensuring that even a marginal increase in gas or dust will stand out against the background. The goal is simple: no ambiguity. If Atlas begins to outgas, the world's instruments will catch it. If it stays silent, the results will be just as decisive. The next few months will bring a rare collective test of both technology and theory, with each observation ticking down the clock toward a clear answer. Photometric data from the months surrounding perihelion added a new layer of complexity to the Atlas puzzle. As the object drew closer to the Sun, its brightness did not follow the gentle, predictable curve seen in typical comets. Instead, light curve analysis revealed a dramatic surge, an increase that tracked with an R to the -7.5 power law. For context, most comets brighten at a much slower rate, with slopes between -2 and -3. Atlas's steep rise is not a subtle statistical outlier, it is an order of magnitude sharper than the standard, and it persists across independent datasets. No known comet in recent memory has followed such an aggressive brightening profile without erupting into a sprawling cloud of dust and gas. Color measurements deepened the mystery. Near perihelion, Atlas shifted toward the blue end of the spectrum, a result that stands at odds with the physics of cometary dust. Dust grains, especially those ejected by solar heating, tend to scatter red light more efficiently, giving comets a warm, ruddy glow. A blue shift can hint at hot gas emissions or an unusual surface composition, but neither scenario matches the absence of a visible coma. The blue color was measured using both ground-based photometry and space-based instruments, ruling out calibration error or atmospheric effects. It is a persistent physical property. Not cometary. These photometric and color anomalies do not fit comfortably within the framework of natural cometary activity. A steep R to the -7.5 brightening curve and a perihelion blue shift, in the absence of a dust coma, strain the limits of current models. The numbers themselves serve as independent evidence. Whatever is driving the changes in Atlas's appearance, it is not behaving like any ordinary comet. Each new measurement widens the gap between expectation and observation, stacking anomaly atop anomaly and forcing scientists to reconsider what is possible for an interstellar visitor. 9 distinct anomalies now stack up against the standard comet playbook. First, 3. I-Atlas arrived from a trajectory almost perfectly aligned with the plane of the solar system, a statistical longshot for any object ejected at random from another star. Then came reports of a jet pointed toward the Sun, not away, a direction that defies what solar heating usually triggers on a comet's surface. The object itself is unusually large, with an estimated diameter of about 6 kilometers, and it is moving faster than interstellar ejection models predict for bodies of this size. Its closest approaches to Mars, Venus, and Jupiter cluster together in time, while Earth's view was blocked at perihelion, a pattern that stands out against the backdrop of random solar system traffic. Spectroscopic analysis adds more weight. The ratio of nickel to iron in Atlas's composition appears far higher than what is found in solar system comets or asteroids, raising questions about its origin. Water, the main ingredient in most comets, is strikingly scarce, just 4% by mass, compared to the usual 50% or more. Light scattered from Atlas shows a polarization profile that does not match any known cometary dust, and its arrival direction aligns closely with the region of the famous 1977 WOW signal. Finally, the object's color near perihelion shifts blue, a hue rarely seen in dusty, sun-warmed comets. Each of these oddities might be explainable alone, but together they form a pattern that is hard to ignore. The sum is more than the parts, and the debate over Atlas's true nature grows sharper with every new measurement. Avi Loeb, a Harvard astrophysicist, has become one of the most visible scientific voices in the debate over 3I Atlas. His approach stands out for its clarity. Treat the data as a checklist, not a puzzle to be forced into a familiar shape. Loeb does not dismiss natural explanations out of hand, but he insists that each anomaly be weighed on its own terms and that the sum of improbable features deserves direct attention. For him, The process is not about reaching for sensational answers, but about refusing to ignore what the evidence plainly shows. In practice, this means applying a strict, step-by-step methodology. When a comet-sized object accelerates without a visible coma, Loeb asks, does the observed push fit the physics of outgassing or not? If a jet points toward the sun rather than away, is there a known mechanism that can account for it? When the nickel-to-iron ratio stands out, or the trajectory aligns with the ecliptic against the odds, each item is logged, tested, and cross-checked against models. The standard of proof remains high, but the rules are simple. Let the observations drive the theory, not the other way around. Loeb's checklist is not a call for extraordinary conclusions, but for transparent, falsifiable criteria. He argues that science advances by setting clear decision points. If a coma appears at the predicted brightness, the natural model holds. If not, the field must be willing to consider alternatives, including technological possibilities. The goal is not to speculate, but to follow the evidence without prejudice wherever it leads. In the case of 3I Atlas, this means the coming months will serve as a public test of how science handles the unknown. Science demands clarity, and 3I Atlas offers one of the cleanest decision points in recent memory. The coming observation window is not about subtle interpretations or wishful thinking, it is about meeting hard, measurable criteria. Here is the checklist. Does Atlas, during its closest approach, develop a bright, extended coma? The threshold is not vague. If telescopes, from the Hubble Space Telescope and the James Webb Space Telescope to leading ground-based observatories, detect a cloud of gas and dust with surface brightness exceeding 20 magnitudes per square arc. Second, spread over at least 10,000 kilometers. The natural outgassing model stands. If spectra pick up clear emission lines from water vapor, carbon monoxide, or other volatiles at rates matching or exceeding 10 to the 29th molecules per second, the case for comet-like activity is confirmed. If dust, micron to submillimeter in size, appears at levels consistent with billions of tons lost, the answer is clear. But if the sky stays quiet, no coma, no strong gas lines, no dust at the necessary scale, then the numbers leave no room for ambiguity. Natural outgassing cannot explain the measured push. The checklist is binary, coma and gas, or none. By the end of January 2026, the data will be in. Science moves forward by setting rules and sticking to them. For Atlas, the test is simple. Watch for the coma. Measure the gas. If both are missing, the field must look beyond the familiar. Right now, the universe hands us a test. Trust the data or cling to comfort. As telescopes around the world fixate on Atlas, the evidence will either rewrite what we know or reveal how little we understand. In the coming weeks, nature or technology will speak. The real frontier is not out there, it is in how we choose to listen.